And we just might have had the most consequential week in terms of politics and science in a long time. Could be the week of the year. Friedberg's been going nuts inside the group chat because everyone is trying to replicate this LK-99 room temperature semiconductor experiment. Superconductor, yes. So, God, I mean, this has been, what has it been, like 10 days? And now everybody is on Twitter trying to recreate this. Maybe I should just let you cue this up, Friedberg, since this is the first time, perhaps the last, that we're going to start the show at Science Corner. So Science Corner Takeover Week. Tell us, is this legit? Because you flip from this is a fraud to this is changing the world. Like every day, you seem to have a new piece of evidence. Where are you today with this? Is this the real deal?
It's probably somewhere in the middle, but it leads to a path that could get us to the Holy Grail, which is room temperature superconducting material, which we've talked about twice on the show before. And I encourage folks to go look at the episode we did a couple ago after the original claim was made a few months ago that turned out to not be true. But the description in the paper that came out on how to make this material was chased by hundreds of labs around the world over the last few days. Folks have been live streaming it on these Chinese websites, Bilibili and Twitter and Twitch. Everyone from Russian scientists to Chinese to Korean to American to European. I will say one thing that I think is really profound, which this is the first time in a very long time that I've seen so many people share a unified voice about optimism, about an abundant future, optimism about a big breakthrough, rather than get on social media to share a voice about fear and anger at someone or something, and to hear everyone around the world get together and be excited about the potential of this discovery and its applications. It's really profound to see, and it's really amazing and wonderful to see. Now, where we are, a bunch of labs took the described chemical structure of this material, LK-99, which has lead and phosphorus, oxygen, and some copper in it, and put it into these modeling systems, these computer modeling systems, to try and understand where do the electrons flow, where do the electrons sit in this material, if this material is made the way it's described. And 5 different labs have now published papers that show that the way that this material is supposedly produced, it should create these pathways or these energy states with the electrons that theoretically could enable superconductivity at a very high temperature. And so that's a very confirmatory signal that computer modeling of the electron clouds, because remember, electrons, even though they move around the nucleus of an atom, we only kind of have a probability statement of where they are. So if you look at all the probability statements of all the atoms stuck together and you try and figure out what's the aggregate probability of where electrons are, it indicates that there are these pathways that theoretically could allow for electrons to move freely through the material and be completely void of any sort of resistance, which is superconductivity. And so that's what's really profound about the modeling outputs from 5 very separate independent labs.
Just so we're clear, when electricity normally moves down an electric wire or in computers and CPUs, GPUs, whatever, there's resistance. That resistance results in loss. It results in heat. And the only way we've been able to reduce that loss is by making it freezing cold, like significantly cold.
Totally right. Yeah.
So now, if we were to do this when we didn't have to make it cold, that means that these superconducting experiments move from the laboratory where it's forced to be cold to the real world. Our desktop, you used an analogy in chat that I thought was really interesting of like a superconducting road where, and then you don't lose energy. Right now, how much energy do we lose transporting it to our houses?
Right. So, I would say on the order of 70% of energy we produce is lost to heat and friction. Think about moving a car down the road. When you move a car down the road, you're having to put energy in to overcome the friction of the car hitting the road. So if the car could hover above the road, the friction goes away and the energy needed to move the car goes way, way down. When you build a data center, the electrons that are moving through the copper and the semiconductors bump into other atoms. When they bump into the atoms in the material, they shake those atoms. When atoms shake, that is heat. So that's why copper wire heats up when you put electricity through it. You're moving electrons through it. Some of those electrons bump into the copper atoms, shakes the copper atoms, they get hot, and then some of the electrons make their way through. The rate at which electrons are bumping into other atoms is the resistance of the material.
So,
so all this energy is going into cooling down data centers, and all this energy is lost in computing to heat. And same in electric motors could be reinvented. Semiconductors, integrated circuits would be reinvented. And like I said, if you had enough of this material, you could put it in roads. And because superconductors also reflect magnetic fields, you could put magnets on the bottom of cars and float them above the ground and cruise around without any friction.
And so if any of this is true, this 70% loss of, and then all this energy put into cooling data centers, we could be looking at doubling or tripling the amount of energy available because we've built a certain amount of energy infrastructure. So this would be all gains if we could figure out how to leverage this technology. Massive gains and massive abundance. It would lower the cost of electricity by 10%, 100%.
I mean, look, assuming huge infrastructure investments, which would take probably decades to do,
sure,
you would get there. But in the near term, there are these incredible applications. Quantum computers are built using little superconductors as the qubit. And so the superconductor holds the qubit state. So this idea that we could now have room temperature quantum computing is also a very profound one, game changer, low cost. And the first thing that would be changed is likely electronic components. So we would take electronic components and redesign them using superconducting material that would allow you to reduce heat loss and energy loss. And that would have a big transformative effect on, for example, the big effort right now to make more AI chips, GPU chips to do matrix transformations.
There is some precedent for this. People are now creating optical bridges between GPUs and CPUs in order to reduce the heat. So they're using optics, basically light, to transfer
fiber
data.
Optic interconnects, yeah.
That's been the big lift right now, from what I understand, in GPUs and data centers is
but you
just
still have to
moving
convert
the data.
Yeah, I mean, we could go on for hours on that, but like, yes, I mean, this would just be a game changer in electronic componentry.
Photonic chips, right? Yeah.
Photonic chips. But look, this is obviously a little bit separate. But here's where we are. So LK-99, there's all these simulation models that show this thing could work. But there's two things I will say came out of this from some of the simulations. The first is, remember, this is a crystal with mostly lead atoms. And these lead atoms, some of them get replaced by copper. And when they get replaced by copper, it causes the crystal structure to change by 0.46 degrees, is what the Koreans say. The angle changes by 0.46 degrees. And when that happens, that bending causes the electrons in all the atoms in the crystal to overlap slightly. And that overlapping effect causes this free-flowing electron tunnel. That is the theory for why this superconducts. Now, what the simulation showed is that you have to replace only one of the lead atoms, not any of the other ones, in order for this to work. And that could explain why everyone's having different results in the lab trying to reproduce this. Because when you bake this stuff in an oven, if the copper gets into the wrong atom space in the crystal, it doesn't work. And so that's why some of these things might end up looking good and some of them don't look good. And some of them, there was a lab yesterday in China that published no resistance, but they had to cool it down to 100 degrees below freezing. And so it wasn't at room temperature, but it did superconduct. It did have no resistance.
170 Kelvin, I think, is where they got it.
Yeah, so 100 below zero Celsius.
So in other words, there is a key. There's a key here in the molecular structure that you have to just thread perfectly.
You have to replace the right lead atom with the copper in order for this to work. And so that's a technically very... And what happened, by the way...
So that's a fidelity issue? That's a tool issue? Like you have to have the right tool to do it? Or is it luck? Or... Right now.
So here's the crazy story, and I'll tell you guys this. I don't know how real this is, but the guys claim. So remember, these two scientists, Lee and Kim, supposedly saw this material in a lab in 1999. That's why it's called LK, Lee and Kim 99. And so in 99, they came across this, and they could not replicate it, and they had no idea how to make it again, and it disappeared, and they didn't have the sample again. They then spent the next 20 years of their life. One was a college professor and the other one worked for LG as a battery engineer. And they just had these random, normal, everyday lives. It reminds me of Dennis Quaid in the movie The Rookie, where he had like this amazing arm and he was going to go to the MLB. And then something happened and he spent the rest of his life as a high school PE teacher. And then 20 years later, he gets his arm back and he goes to the MLB and he plays in a Major League Baseball game. Because all of a sudden, during COVID, these guys got some funding. They set up a company. They went into a lab and they rediscovered this material. And apparently, this is the rumor. I don't know if this is real. The rumor is they were baking it in an oven in a vacuum sealed tube. And when the guy took it out of the oven, he accidentally bumped into a table and the tube cracked. And when the tube cracked, it did something to the material And then they measured it and, oh my God, it's room temperature superconductor. That's the current theory of the rumor of what happened in the video.
It's like Peter Parker being bitten by a radioactive spider. I mean, this doesn't make any sense.
Yeah. So here's the drama. This guy, Kwon, got inserted to oversee them as like their CTO. The guy that gave the money to Q Center said, he's got to oversee you. Kwon apparently got fired from his job in March, and he was kicked out of this company, was no longer affiliated. And the rumor is that Kwon took all the lab data, and these guys, in 2020, during COVID, they discovered this. They started filing patents and working on the manufacturing process, trying to figure out how to replicate it and do it again. So they had all this data, but they weren't going to publish it. They didn't want the world to know about it yet. And then all of a sudden, Kwon gathers all this data, probably disgruntled after getting fired, puts it into a paper and puts it on the internet. So that's the first paper that came out.
Because there's a website called ARXIV. Is there a pronunciation for this website?
So this is where you can open source file scientific papers, right?
Okay, so this is a place for dropping papers outside of the
traditional
academia?
journal. Yeah. The traditional journal process requires peer review, and there's editors at the journal that decide whether or not to publish your paper. So sometimes
gatekeepers.
Gatekeepers. And so if you don't want to do that, you just want to get a story out to the world right away. So during COVID, everyone was publishing on the site all their updates on research they were doing to help the world figure out what's going on with COVID. So it's a great place to just hit the world with your data, hit the world with your findings.
This is like acoustic raw papers, and it's called Archive. ARXIV.org if you want to go see it. Archive.
So anyone can publish a PDF. No one knows if it's real or not. It hasn't been peer reviewed, etc. So this guy, Kwon, so Kwon drops the paper with his name, Lee, Kim, and Kwon on the paper. Only 3 people can win a Nobel Prize. So the theory is he did this to get his name out there to make sure he could lock in his name for the Nobel Prize.
Wow. Juicy.
And then within a day, Lee and Kim and 4 people they've been working with, including some folks in the US, published another paper with better data, but it was also rushed out. And so both papers are pretty ugly, I got to be honest. They're like pretty messy. They don't have a great deal of clarity. There's errors in them. There's mistakes. There's redundancy. There's little basic chart editing errors, stupid stuff. Clearly, this was a rushed job. But these guys rushed out and said, you know what, if this is going to be public, we now have to correct the story and say what happened. So they put this thing out there.
They wanted to get their claim in to get their Nobel Peace Prize, which would indicate that would lean towards a piece of evidence, as would people funding them 25 years later. That would indicate maybe there's something there.
2 things worth noting on the simulation stuff. Number 1, obviously, you got to get the copper in the right place. And the production way to do that, how do we actually engineer that to happen? It's not really clear. Baking it in an oven clearly is creating what's called heterogeneous results, meaning everyone's getting different results around the world that have been doing this for the last couple of days. And everyone's really confused. Is this real? Is it fake? I don't know. But that simulation explains why there's maybe lots of different results. Another comment, it turns out that one of the simulation teams said, hey, if you put gold instead of copper in the spot, it's a better superconductor. It could actually be a better material.
Oh.
So it's opening up all these paths for exploration that we had never considered before, that there's this whole new approach to creating superconducting materials that was not on anyone's radar before. So this is opening up a whole new realm. And I think this is going to unfold over the next couple of years with more material discovery, more invention coming off of this initial discovery and simulation model that then offers all these other opportunities for creating potentially new materials that maybe are easier to manufacture and better to produce. And the final thing I'll say is that there are some teams that are commenting that are saying that this thing may be superconducting, but only on one dimension, which means along a line of atoms or line of molecules in the material. So normal superconductors, think about them as like a 3D matrix, and the electrons can flow freely through any direction through the matrix, through the crystal. And in this case, they're saying the electrons can only flow freely across a line in this material. And so now there's another question of, wait, how do you manufacture lots of lines to run in parallel to make this thing truly superconducting at scale? So that's all the hard technical stuff that's emerging right now. Whether or not this actually does turn into a room temperature superconducting material that can be industrialized and used in all these applications everyone's really excited about, I think it's probably months to years away from knowing. But at this point, there's a great set of indications that, oh my God, we might be onto something new. There's a whole new path of discovery, a whole new path of engineering and invention. And it's amazing to just see everyone gather around this and get so excited about it, because it really will change so much about the world and create extraordinary abundance and prosperity for humanity if this proves to be real and industrializable and scalable.
Chamath,
can I just ask a simple question here? Yeah, when you say if this proves to be real, if nobody has reproduced the result, why is there any belief that this is real?
There are properties of this that
Look, I think we have to take a step back. We have found superconductive materials in the past. There are many ceramics that are superconductive. Mercury is superconductive. There's all kinds of elements and materials and compounds in the physical world that we've already figured out have these properties. So this is not like a new thing that's never been found before. It's just this idea of trying to find it at a certain temperature where it could exist naturally in the normal world without all this expensive cooling. Okay, but there is a separate thing, which is that we also have found a whole bunch of materials that look and behave like superconductors, but are really not. They're what's called just diamagnetic. And I think right now, what people are trying to sort out is this a clever diamagnet? Is this diamagnetism? Or is it superconductive? And these are huge differences that swing this from, yeah, it's kind of a cool thing, and yeah, whatever, there's a bunch of other materials we found that are like this, to, wow, this is transformational. And right now, we don't know any of that. And I think that all of the mystery around this is mostly because people can be on one side of the debate or the other literally by the second based on what new simulation or what new piece of research people are putting out there. But you have to remember, like, diamagnetism is like a property of matter. Superconductivity is a state of matter. It is totally different. All superconductors are diamagnetic, but all diamagnets are not superconductive. So we could just be extremely excited about not much of anything, or this could really be a breakthrough.
If what the Chinese guys said is that they were able to cool this thing down and get it to be superconductive, then that does...
At 170K, it doesn't mean much, in my opinion.
Right. It's not room temperature, but it does indicate that this material can be superconductive.
Look, there are many materials like this. There's like a lot of forms of red matter that we've already found that at that temperature gradient, at that range of temperatures, can be superconductive. It's not practically useful at that point.
Yeah, that's right.
I don't think you're going to see like some massive revolution. So I'm a betting man. I make bets. I think I've talked about when there was this guy, Ranga Diaz, that had to try this stuff, and he was sort of refuted in what he was working on. But 18 months before that happened, I was trying to get a deal done with the University of Rochester to buy all that IP. So I've been grinding in and around this space for a couple of years. My intuition on this is that this is diamagnetic. And that I think we're going to find that, you know, it's like yet another material added to the list of materials, and it's okay. But hopefully what it really does is it sparks an interest in a lot of other people putting more money behind this.
Nick, if you could pull up this manifold markets, there's a prediction market called manifold.markets that people have been sharing a link from. Betting markets, where people bet either side of this. Will LK-99 room temp, ambient pressure, semiconductivity preprint replicate before 2025? And you can see it's about 30% chance. What do you think of the prediction markets assessing this, Friedberg?
Yeah, I think that's probably a good handicap for where we are. I'll say, when you look at a diamagnetic material, and so what that means, a diamagnet will expel magnetic fields of both polarities. A paramagnet will reflect the north or the south pole. Its north pole will reflect the north pole of another magnetic material, right? Diamagnets, you can put north or south pole and they reflect both. And there's plenty of videos you can watch of putting a frog in like a 10 Tesla machine and the frog floats. Technically, a frog is diamagnetic. But what happens typically with diamagnetic materials is they orient themselves while they're freely floating into a particular direction. So there's going to be three things people are going to be looking for in terms of confirmatory proof on LK-99. The first is, does this material float like a superconductor over a magnetic field? Because remember, superconductors perfectly expel magnetic fields. They are dimagnets to the absolute degree. They perfectly reflect all magnetic fields. So if you put a superconducting material above a magnetic field, it should kind of float freely and spin around and stuff. If it orients back to one position, it probably means that there's something going on where it's maybe not a perfect superconductor. Now, all these the second thing you're going to look for is zero resistance. So can you actually pass an electric charge through it and have no resistance in the material? So you're seeing data coming out now that's indicating we're seeing that, but we're seeing it at a low temperature. No one's yet replicated this at room temperature. And the third thing is a transition, which means that there's a point where it shifts, because that's a classic characteristic of superconducting materials. If there's a transition temperature, transition phase, where the material becomes superconducting or it's not superconducting. So those kind of generally, those three experimental proof points are what everyone's looking for. Thus far, the videos we've seen look like UFO or Bigfoot videos. They're friggin' grainy. They're like, you guys have seen some of these videos that have come out. They're like at a distance. It's like, wait, why didn't you do the whole angle? Why did you only take a picture? Why didn't you do the video? There's this woman in Russia who's a scientist.
We're now in UFO territory. People are jumping
look at this. I mean, it's super, like there's a little flake of, here's a video of a little flake of a material that someone supposedly made in the lab.
Or it could be dust on the camera.
Right, and they put it over over a very strong magnet, and this is the video they got. It's super blurry. There's a woman in Russia, and she totally reinvented the manufacturing process. She's actually a well-known scientist, so she's not BS. And she said, I made this thing in my house using a furnace, and I used a whole new process. So she does this whole new process. She live streams the whole thing. And then she puts out a video of the thing floating in a straw. A video photo, and it's a blurry photo. And people are like, show us the video, show us that it's real. And she's refusing to. So this whole thing is feeling a little like there's UFO, Bigfoot type people out there that we're not really seeing clarity on, is this real? And then obviously the resistance data, there's very credible academic universities coming out. And I will also say there are a number of labs. There's one in China, and the one in China that measured the zero resistance at negative 100 degrees, they created 8,000 samples. So they found one that worked. There's another lab that did 8 different pathways of manufacturing it in China, and they said, we can't find any that work yet. So, there's a lot of negative indications as well, which is why the prediction markets are probably right. But I do think that this theoretical explanation that you have to get the copper atom to replace the correct lead atom in the crystal structure explains a lot of the heterogeneity in results and the reason why people may not be able to replicate this. And if someone could crack the code on how do we actually engineer this thing and produce it correctly based on the theory, maybe we'll see different, better results. But again, that's also theoretical because no one seems to have nailed a manufacturing process here. So lots of data coming in every day. By next week, we could be clapping and cheering, or we could sort of be on this very long grind, sort of like Russia, Ukraine, just a long grind, and it'll last years. And maybe someone will win, maybe someone won't, or maybe it just opens up a whole new set of explorations for new superconducting materials at room temperature that could change the world.
I gotta say, the thing I love most about this is like we have this Oppenheimer film comes out, and at the same time this happens. We got UFO testimonials, in congressional hearings, all of this energy at the same time of people who are just really stoked to do material science, to do basic science, to figure out big problems. And I agree with you. The optimism around all this is I mean,
tell me something else. Tell me something else in our lifetime, in the last decade or two, where we've seen the whole world say in a positive way, something great could happen instead of something bad could happen and someone's to blame for something. I mean, it really is, in my mind, the first time I've really seen this happen in a very long time. Maybe the internet was a
I would say the
kind of great moment.
What came to mind. Yeah, everybody being connected, everybody being able to share information
from all over the world. They're doing it on Twitter and Billy and YouTube and like all sharing this stuff and saying, "My gosh, we could have this breakthrough together as a species, not like a country, not a individual, not a who messed up, who did something wrong, who's to blame, who's on the other side." It's like, dude, if this happens, we're all going to be like chilling on the beach. It's going to be amazing. Like, this is awesome for all of us.
We're going to have a rash of VCs running into this next and start funding this stuff, material science.
Yeah, I mean, my attitude is kind of like, wake me up when you know it's real. Mm-hmm. Because, Friedberg, it's nice that if this is real, then it's great that there's all this positive energy around it, but that's like a big caveat. Until we know that there's something real here, I think it's premature for everybody to say that this is like some wonderful thing. Now, if we find out that the science is real and then it's just a debate over commercialization of it, then I agree. That would be like a really positive moment.
I just love the fact that when something positive in the world happens or when something negative happens, we have this amazing platform for everybody, social media, X.com, formerly Twitter, where everybody can get together around this campfire and just start discussing it and speculating. Now, some people don't like speculation. Obviously, if there's a school shooting or a tragedy, a building burns down, the fog of war, as we've seen in the constant Ukraine coverage, you can have, it's very easy to make mistakes when you're hashing this stuff in real time. But I love the real time nature of the world and the pace we're moving at. It's kind of delightful
I
to me.
don't have a problem with the speculation, and there is a fun element to it. But when you start talking about investing in it, like I said, wake me up when you know it's real.